In this video, we will be comparing how the graph of a function relates to the graph of its derivative. So we're going to start off with a little warm-up by finding the derivative of f at x. So f at x is this polynomial, x cubed minus x. So I am first going to find f at x plus h and just simplify it. So just a reminder that x plus h cubed means x plus h times x plus h times x plus h. So I'm going to rewrite the first one, and then I'm going to do my distributive property here. So we're going to have x squared plus xh plus xh, so that's two of them, plus h squared. And then I'll distribute the negative into x plus h to get minus x minus h. And now a final distributive property here, so multiply the x into the entire bracket, so x cubed plus 2x squared h plus xh squared, and then multiply the h in. So plus x squared h plus 2xh squared plus h cubed minus x minus h. And if we look at this, some things do collect. So we'll have x cubed, we have 3 x squared h's, and we have 3 xh squares. All right, and now let's use that first principles. So the derivative is equal to the limit as h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h minus x cubed minus x all over h. So x cubed minus x cubed cancel, and then negative x minus negative x, so that's negative x plus x, those cancel. So we're just left with these three terms and the negative h. They all have an h in common, so I'm going to factor that out, and we're left with 3x squared plus 3xh plus h squared minus 1 all over h. The h's cancel, and then if I sub in 0 for this h and this h, our derivative is just 3x squared plus 0 minus 1. So I'm going to graph f at x, and I'm going to graph its derivative and then make some observations. So f at x is equal to x cubed minus x. So using previous knowledge, I'm going to first factor this. So I'm going to have x and then x squared minus 1, and then a difference of squares here. So x plus 1, x minus 1. And now I know my zeros are -1, 0, and 1. And I'm actually going to remove the scale on the y-axis because we won't actually know the max and mins accurately. So with this, I also noticed that we have a positive leading coefficient. It's an odd degree, which means we're going to go from quadrant 3 to quadrant 1. So just a rough sketch, just the shape of it. But I don't actually know where the max and mins are accurately as of right now. Next, I'm going to graph the derivative. The derivative is 3x squared minus 1. I can't factor that, but I do know that the vertex is at -1 because that is technically in vertex form. I can also solve for the zeros by setting the equation equal to 0. Move the -1 over, it turns positive. Divide both sides by 3 and square root both sides. And then if I just rationalize this, because this would be plus or minus 1 over the square root of 3, it'll become this, okay? And that's less than 1, so wherever those points are, my parabola is opening up like this. Here we are. So here's the original f at x, and here's its derivative. Now, there are a few features we should know. when the derivative is equal to 0, that would mean that the slope of the tangent line is 0 as well. Now, what points on f at x would the tangent lines be 0? At the max and mins. So that's a really nice, interesting feature, that the derivative is equal to 0, then we have a max-min point. So now we can actually accurately graph where those max-mins are. They're going to be at plus or minus root 3 over 3, and I can plug that point into f at x to actually get the optimal values. Next, when my derivative is in the positive region, so from negative infinity to that 0, and from that 0 to positive infinity, that's also the same time where the function is increasing. Because if the derivative is positive, then the slope of the tangent lines must be positive as well. And that would give us an increasing function. So when the derivative is greater than 0, f at x has an interval of increase. Likewise, when we have the derivative in the negative region, the actual function is decreasing. So when the derivative is less than 0, f at x has an interval of decrease. And finally, when the derivative has really, really large values, whether they're really large positive or really large negative values, that is when the slope of the tangent lines will be the steepest. And those values, if we look at our parabola, the absolute value of the derivative is greatest as we approach infinity, because these go up forever. So the tangent lines on this function will be the steepest as x approaches infinity and x approaches negative infinity. And the times where the derivative is closest to 0, so around the zeros, a little bit when they're positive, a little bit when they're negative, that's when those tangent lines will be the most shallow. So with these observations in mind, we're going to go back and forth between getting the original function and trying to draw the derivative, and vice versa. So let's take a look. Sketch the derivative for each function. So the graphs that we are given are, let's say, f at x, and we need to graph or sketch a possible derivative. So the first thing I'm going to look for is those max and min points. I have max and mins at -1 and 1, which means on the derivative, those must match up with the zeros, because that's where those tangent lines will be horizontal. Next, I want to see when the derivative is going to be positive, and that relates to when the function is increasing. So here, up to that maximum, our function is increasing, and all those tangent lines have a positive slope. So we should have something like this. And once we get past the minimum, we're increasing again. So this should also be in the positive region. This is the only portion between -1 and 1 where our function is decreasing, and that would correspond to our derivative being in the negatives. And here we are. Now, it's not an accurate depiction of the derivative, but it's just a sketch of when the derivative would be positive, negative, when it would be 0. For the next one, once again, I'm going to start off by looking at max and mins. Here, here, and here. So I'm going to plot those as zeros on the derivative. And I am estimating a little bit here. Now, if it was hard to visualize the increase, decrease, positive, negative intervals, we can also create a little bit of a number line to help guide us. So what you want to do is plot your max mins. So 0, I'll just say approximately, it's not exactly 1.5, so I'll just say 1.4 and -1.4. Now, when we're going from negative infinity to negative 1.4, our function is decreasing. If our function is decreasing, the derivative must be negative. Then our function starts to increase. So if it's increasing, all those tangent lines will have positive slopes. Then it starts to decrease again, so back in the negatives. And then we start to increase again, so back in the positives. So now we can take that and draw our sketch. So we want to go from negative to positive to negative to positive. So we're just going through our zeros, and this fits perfectly. We start off in the negatives, then we go to the positives when it's increasing, back to the negatives, then back to the positives for the end where it is increasing. Next, we have an absolute value function. So as a reminder, right here where that direction changes, we will not have a derivative. It is not differentiable at x equals 3 because we have that little kink. Okay, so we're going to have a hole there for our derivative. So if we look to the left of 3, this portion here, it's always increasing and it's a line. So my tangent line and the actual function itself, it's the same thing. And if you calculate the slope when x is less than 3, rising 2, running 1, the slope is 2 everywhere along that line. So when we're less than 3, if the slope is positive 2, I'm going to put a hole, and here we are. The derivative will always be 2 because the slope of the tangent line at every point when x is less than 3 is positive 2. On the way down, if we count our slope here, it's negative 2. So a horizontal line, because it's the same slope of the tangent line for the remainder of that absolute value function, it's at negative 2. Finally, we have another function here that has this vertical tangent. So at x equals 2, it'll not be differentiable. Now, let's see what is happening here. As we're approaching negative infinity, this is getting more shallow. Then as we get closer to 2, it's getting steeper and steeper. As we're past 2, we're really steep, and then we shallow out. And this entire function is increasing. So I'm not going to see anything in the negatives for my derivative. So I'm going to give myself a little asymptote here for my derivative. And like I said, nothing in the negative, so I don't expect to see anything there. And we start off with really shallow slopes, so really small. Then, as we get closer to 2, the tangent lines are more steep. So here we are. When we're past 2, we start with very steep tangent lines, and then they get more shallow. So here is a potential derivative for this function. Now let's go in the opposite direction. The sketches that we're given are the derivatives, and we need to come up with a possible function. So now I'm looking at, well, where are the zeros? Because wherever the zeros are, that's where we're going to have a max or a min. I'm going to try that number line method again. So my zeros are negative 2 and 2. And when we're to the left of negative 2, we have a positive derivative. And when we're to the right of, 3, we also have a positive derivative. It's only in between those values that we have a negative derivative. So what does that mean? When the derivative is positive, our function must be increasing. And when it is negative, it must be decreasing. All right, that gives me something to play with. So I need to increase until I get to negative 2. And I mean, I'm not going to draw anything accurate here. So I'm just going to put a random point at a maximum. And then I need at x equals 3 to have a minimum. So maybe something like that. This shape would follow this derivative. Next, our derivative is just a line. And it has a 0 at positive 3. If I were to use my little number line, to the left of 3, the derivative is positive, so the actual function will be increasing. To the right of 3, it is negative, so it will be decreasing. That's going to be a parabolic shape. So for example, let's say that's going to be my maximum. There we are. Next, our derivative is a horizontal line, and this horizontal line is at -3, which means every slope of the tangent line will be -3. Well, the only way for the tangent line to always be -3 is if the function itself is a line with a slope of -3. So I'm just going to draw a line going down, and I'll make a note that the slope must be -3. Can't really draw that accurately because I don't have any y values there. I also don't know where the y-intercept should be. I'm just getting the shape. And finally, the last one. Well, clearly the derivative cannot be found when x is 0. So we must have maybe a cusp, a vertical tangent, and discontinuity there. And we're only in the negatives, so the function will always be decreasing. And we're going to start really shallow, then get really steep, continue being really steep, and then turn really shallow. So this must be a vertical tangent at 0. And we're decreasing. So I'm going to start higher, shallow, then vertical tangent, and then continue. Something like that. Okay, so here we've just been practicing using the features of the derivative to try to come up with a function that could match it. Now, like I said, the actual functions we're drawing, they're not accurate in the y coordinates or the placement of the max or mins. We're just trying to get that shape of the functions or the derivatives when we're given the function itself.